Good morning, everyone. This is Julie McDonald with Microcom Technologies, and I'd like to thank all of you for attending today's webinar with MetaGeek. Today's host, Joel Crane, will be presenting today, and if anyone has any questions, please feel free to submit them in the question box, and Joel will answer them at the end of today's presentation. Joel, I'm finished for now, so you can take over.
Great, thanks Julie. Welcome to Visualizing Wi-Fi with Channelizer and IPA. In this webinar, I kind of wanted to talk about how spectrum analysis and how packet analysis relate to each other and how you can see how they relate to each other with Channelizer and IPA. Just kind of a quick introduction so you know who I am. My name is Joel and I am the technical trainer at MetaGeek. I do things like teach webinars like these, write training materials, make YouTube videos, things like that. And like Julie said, if you have any questions throughout the webinar, please feel free to use the question tool to go ahead and ask those, and we'll answer any questions that you might have at the end of the webinar. If you need to get in touch with me, you can always reach me on Twitter. Twitter is where the Wi-Fi community tends to hang out, so that's a great way to get a hold of me if you need to get in touch for any reason. And with that, let's go ahead and get started. Now, I want to cover some quick basics before we jump into the complex stuff. The first thing I'd like to talk about is the half-duplex nature of Wi-Fi. Now, to help you understand what the half-duplex nature of Wi-Fi is, I want to stop and think about Ethernet for just a moment. If you look at an Ethernet cable, with an Ethernet cable, you've got multiple twisted pairs of copper inside the cable, and that allows one cable to send traffic in two directions at the same time. You can send traffic to a switch and from a switch to a machine simultaneously, so it's kind of like a two-lane highway. Wi-Fi, on the other hand, is like a one-lane highway. We can only send traffic in one direction at a time. So here's what a wireless conversation looks like. Let's say that we have an access point. If that access point needs to send some data, the first thing it's going to do is it's going to do a clear channel assessment. It's going to listen to see if there's anything talking on the channel. And if there's nothing using that channel, then the access point will go ahead and transmit its data to the laptop. Now the laptop's going to take a look at that data. It's going to inspect that data and make sure that it understood it. And if it understood what it just heard, then it'll go, yep, check, I just understood that, and it will reply to the access point with an acknowledgement. We call an ACK for short, to let the access point know that, yep, check, we received that data and we're good to go. Now there's a couple of things that can go wrong here. One thing that can happen is if the access point performs its clear channel assessment, and if it hears that there's something else talking on the channel, it knows that only one device can talk on a channel at a time, so it's going to have to back off and be quiet and wait for an opportunity to talk. Another thing that can happen here is the access point might transmit its data, but then that data might get interrupted by something else. If something else starts talking on the channel, it might corrupt that transmission. And so by the time it arrives at the laptop, it's just a bunch of garbage, and the laptop can't understand what that transmission is. And if the laptop didn't understand it, it's not going to send its acknowledgement. So the next thing that would happen in that scenario is the access point would start to go, okay, well, I haven't heard that acknowledgement back, so the laptop must not have received the data frame. So the access point is going to transmit that data again and again and again, and it's going to keep trying to transmit that data until finally the data makes it through to the laptop, and the laptop can go, yep, check, I received that data, and reply with an acknowledgement. This is known as a retransmission, and it's actually a lot like my 2-year-old daughter in this way. I've got a daughter that's about 2 years old, and she's just getting to the point where she's talking a lot. You know what I'm talking about, right? If you've ever had kids or been around kids, or maybe if you've just seen some kids from a distance, you know that they're kind of like a wireless device in this way. If she tries to say something to me, and if I don't send her some kind of acknowledgement, if I don't acknowledge that she said something, she's just going to repeat herself over and over and over and over again until finally something makes it through to me, and I can send her some kind of acknowledgement that I received, I heard what she said. So Wi-Fi is a lot like a toddler in that way, and if you've been around toddlers, you know that that's true. Now we know that now that we understand the half-duplex nature of Wi-Fi, we have to kind of zoom out a little bit. We have to back up a bit and think about, instead of a conversation between one device, maybe one client device and one access point, we have to think about the whole channel. If we have an entire channel full of devices, all of those devices have to take turns talking. So for example, if we've got a phone that's transmitting some data to the access point on that channel, all the other devices on that channel have to be quiet and wait for their turn to talk. Only one device can talk on a channel at a time, and that includes other access points from other networks that are on the same channel. It can be your own access points on your network if they're all stacked up on the same channel. It can be neighboring access points that are on the same channel. It doesn't matter. Only one device can talk on a channel at a time. And if you put too many devices on the same channel, they are going to run out, that channel will run out of capacity. You will run out of opportunities for things on that channel to talk. We also have to worry about non-Wi-Fi interference as well. We all know that especially in the 2.4 gigahertz band, there's tons of non-Wi-Fi devices that use that same frequency space. Now, a microwave oven is just one classic example. There's tons and tons of other devices that operate in the 2.4 gigahertz band, like cordless phones, wireless video cameras, baby monitors, Bluetooth. There's all kinds of things out there that can cause interference. And the problem with these devices is if you have an old microwave oven that likes to spew out a little bit of interference, it might leak out some of its RF activity and cause interference in the 2.4 gigahertz band. When you throw a frozen burrito into the microwave oven and mash the 30-second button like I usually do, then that microwave oven might start spewing out interference all over the channel. And when that happens, all of our Wi-Fi devices that are on that channel are going to hear that activity and throw their hands up and simply back off and be quiet and wait for their turn to talk. The half duplex nature of Wi-Fi, the way that only one device can talk on a channel at a time, includes non-Wi-Fi devices as well. So we have to be careful of that. We have to watch out for interference from those non-Wi-Fi devices. So let's recap really quick. Let's take a look at the three main types of interference. The first type of interference is co-channel interference. Co-channel interference occurs when we have a bunch of devices that are all on the same channel. When you're all on the same channel, every client and every access point on the same channel has to compete for time to talk. And as long as you don't have too much going on a channel, that actually works out pretty well. I like to think of it kind of like a dinner table conversation. If you've got 4 people around a dinner table, then everybody gets plenty of opportunities to talk because there's only 4 people. But if you've got 12 or maybe 15 or maybe 30 people around one giant dinner table, there's so many people that want to participate in the conversation that it gets very difficult for people to get an opportunity to talk. That is co-channel interference in action. The next type of interference is adjacent channel interference. Now, adjacent channel interference happens in the 2.4 gigahertz band when we have access points and networks that are on partially overlapping channels. For example, if we have an access point that's on channel 4 and another access point that's on channel 5 and another access point that's on channel 6, all 3 of those access points are overlapping with each other. And instead of politely taking turns talking like we do with co-channel interference, every access point and every client device on overlapping channels are just going to yell and interrupt each other. It's just going to be a big yelling match. It's kind of like the dinner table analogy like we saw with co-channel interference, but instead of being around a dinner table, this is adjacent channel interference is more like going to a restaurant. When you go to a restaurant, you get a table with your friends and you start having a nice conversation and you all take turns talking, but you can still hear all the other tables around you, and they're not taking turns talking with you. So you talk a bit louder to compensate, and they talk a bit louder to compensate until pretty soon everybody's yelling and having to repeat themselves inside the restaurant. Finally, there's non-Wi-Fi interference. That comes from those non-Wi-Fi or non-802.11 devices. They also need time to talk, but they typically don't have those politeness mechanisms built in that Wi-Fi does. They don't do they don't do a very good job of backing off and taking turns. They will just simply talk over each other. So the next question is, how do we detect interference? We need to figure out how to detect these different types of interference, and there's 2 main ways of doing that. The first way is through Wi-Fi scanning. With a Wi-Fi scanner, we're just going to use a typical normal Wi-Fi adapter to scan for wireless networks, and that gives us some great information about which channels all the nearby access points are using. So, for example, if we look at this screenshot from a Wi-Fi scanner, we can see that there's a couple of access points here on channel 1. They're not very loud. We can see that these boxes aren't very tall, so they're not very loud. We can see there's a couple of access points on channel 6 and a couple of access points on channel 11 as well. But there's also this one access point on channel 8. So it's going to partially overlap with everyone on channel 6, and it's going to partially overlap with everyone on channel 11. And that's really problematic. That's going to cause interference. So we can use a Wi-Fi scanner to do things like pick a better channel for our wireless network, and also to make sure that we've got enough signal strength. But there's some things that we don't get with a Wi-Fi scanner, such as how busy is channel 1 really? Is it being used 10% of the time? Is it being used 90% of the time? We don't know. We have no idea how often that channel is being used. And that's where spectrum analysis comes in. With a spectrum analyzer is a special piece of hardware that shows us all of the raw radio frequency activity in the spectrum. And it shows us two really important things. The first thing it shows us is interference from non-Wi-Fi devices, non-802.11 devices. If there's something like a cordless phone or a wireless video camera there, a normal Wi-Fi adapter isn't going to see that, but a spectrum analyzer can see that activity, and we can go, oh, hey, there's a cordless phone, and that's shutting down this specific channel in this area, and then you can use the spectrum analyzer to locate that device. The other thing that spectrum analysis is really great for, and this is going to be one of the focuses of our conversation today, is it's great for showing us Wi-Fi channel congestion. We can actually look at a channel and see how busy the channel is. We can see what percentage of the time the channel is being used, and that's really, really useful for telling us what is happening on the wireless network. So what I always like to do is I always like to, at least with Wi-Fi and with many other things as well, is I like to start with the physical layer. I like to take a look at the physical layer to see what's happening. Now, what does that mean exactly? Let's think about Ethernet for a minute. Let's say that you've got a machine on the wireless network, a machine on your wired network that isn't able to access the internet. Maybe the first thing you're going to do is check the cable. You might check that cable to make sure that you have continuity in the cable, make sure that cable is working. Now, you could do that with a fancy cable tester, or you could just replace the cable to see if that fixes the problem. That is starting with the physical layer. Now, in Wi-Fi, we don't have cables. It's wireless, right? So instead of looking at the cable, the equivalent to the quote-unquote cable is the air, is the spectrum. So we're going to look at the air with a spectrum analyzer to see what's happening. Spectrum analysis will then guide us to the next troubleshooting step. So it's going to go one of two ways. The first thing that we might see is we might see a non-Wi-Fi signature, like this cordless phone. We might see, okay, there's a cordless phone. It's totally blowing up channel 11. No wonder nothing is working. And that's when you're going to use spectrum analysis to identify and remove the non-Wi-Fi interference. You're going to go get rid of that interference. Now, the other way that this might go is you might see a Wi-Fi signature. You might see a signature that looks exactly like Wi-Fi, like this one here. If you see a Wi-Fi signature with heavy utilization, meaning that the channel is constantly being used, that's when you're going to switch tools. You're going to move to a packet analyzer. You're going to look at layer 2, the packet layer, to dig deeper into that Wi-Fi congestion and look at those conversations to find out exactly what's going on. So what we're going to do now is we're going to go ahead and take a look at this with Channelizer and the Wi-Spy. So to do that, I'm going to switch over to Windows really quick here. I'm going to start up Channelizer. This will just take me a second. And I'm going to start out by showing you what a cordless phone looks like. I've got an old Uniden cordless phone here, and I really like this phone because it creates a nice, strong signature in the 2.4 gigahertz band. So you probably just heard me hit the power button there as we started this thing up. Now, if you look closely right here on channel 9, you'll notice that there's a big red spike shape that started up there. That is the signature that a cordless phone makes. And if we aren't sure whether it's a cordless phone or not, there's actually some tools built into the software here to help us understand what is going on. We can switch over to the interferers tab and go through this library of common shapes, and we can make some comparisons to see whether that matches up or not. Now, if I wasn't sure whether this shape matched up, I could click on that shape and hover my mouse over it in the density view to see whether it matches up or not. And I can see that certainly does not look like an 802.11b shape. However, if we keep looking around here, we can find there is a signature here for a Uniden phone, and if we hover that that shape here, we can see that it matches up pretty much perfectly. So that tells me that this is a Uniden cordless phone. So we know that this is a non-Wi-Fi device. We were able to identify it with spectrum analysis by looking at the raw radio frequency activity, and we can use this tool to go track it down. There's a function in here that allows us to actually go physically locate this device that is causing interference. Now let's take a look at a couple of other things that we can see with the spectrum analyzer. First off, I can see all of this raw radio frequency activity in the spectrum right now. If I disable color by utilization, that's going to leave this blue line. Now, this blue line is showing me all of the raw radio frequency activity that's happening in the spectrum right now. It's current. It's real time. It's showing me what's actually happening at this exact moment. Now, this blue line tells me a couple of things. First off, we can see where the activity is occurring based on which channel it's happening near. So if we look down here at the bottom of the spectrum, we can see that there's a little bit of activity down here below channel 1, and there's a little bit of activity up here above channel 14. We can also look and see that this spike shape is holding very, very consistently right here on channel 9, and that's our cordless phone. The other view that I really like in this tool is color by utilization, which is what I had enabled earlier. This view shows us how often things are talking based on color. So if you look at the colors, blue indicates that something is talking there, but only about 10% of the time. Think of it kind of like this. Blue is kind of like a clap. Listen to a clap. That doesn't really interrupt our webinar at all, does it? Whereas green tells us that something is talking there a little bit more often. Green says that something is talking there about 20% of the time. Yellow indicates that something is talking around 40% of the time, and red means that something is talking there 50% of the time or more. Think of red as opposed to a clap. Think of red as kind of like an air horn. If somebody walked into this room right now and blasted off an air horn, that would completely interrupt our conversation, because an air horn is a very, very consistent, it doesn't stop. It's just very, very consistent, just goes. That's kind of what the cordless phone is doing to our environment right now. So let's go ahead and turn the cordless phone off, and let's focus our attention on another shape that we can see in the spectrum. You can see right here in the waterfall view where I powered that cordless phone off. And as this rolls off of our waterfall view, we're going to see it fade from red to yellow, and there it goes to green, and in a moment it'll be blue, and then it will disappear entirely. If you look on channel 6, you may notice that there's kind of this square, this kind of flat tabletop shape right here on channel 6. That's what Wi-Fi looks like. In fact, if we go look at our signatures tab again, we can actually look and see that there are two forms of Wi-Fi on that channel right now. We can see that there's some 802.11g or 802.11n traffic on that channel. We're not sure which, but we can tell it's one of those. And we can also see that there's some 802.11b traffic on that channel as well by using those two signatures. 802.11b makes a curve shape in the spectrum, whereas 802.11g and 802.11n make a flat tabletop shape in the spectrum. Now, we can see, based on the color, that the taller part of the signature is using the spectrum about 20% of the time. The shorter part of the spectrum is using it about, I'd say, 50% of the time or more. Now, if we wanted to find out which network this is associated with, we could visit the networks table, and we could turn on all the wireless networks that our Wi-Fi adapter is able to pick up. Now, that's a lot, and it's really hard to figure out which is which, so I'm actually going to apply a filter. First, we're going to start out by filtering down to every network that is on channel 6. Okay, so now we know that it's one of those. And then, based on the height, we can go through here and try to figure out which network is causing this traffic. Now, it might be Chalfont here. It could be them. I also know that MetaGeek, we have an access point on this channel as well. And I'm going to say, based on the height of those, it could be one of those two networks, or it could be any of the other ones that are on the same channel. Probably not the ones that are taller, because they just don't quite match up, but we know that it's probably one of those particular access points. Now, I'm going to go ahead and hide those networks again, and I'm going to run a throughput test on this channel to see how much traffic we can generate on the channel. I'm also going to switch over to the channels table, and I'm going to look at channel 6, and I'm going to look at the utilization. Let me make sure that we're set correctly here. Let's go ahead and bump this up to negative 80 dBm. So we we are taking our measurement for how often the channel is being used at negative 80 dBm. That's this signal strength right along here. So if we look at the channels table, we can see on average how often that channel is being used from a percentage standpoint. And we can see right now it's being used about 46% of the time. Now, I have a Google Nexus 7 sitting here. It's an old Android tablet by Google. It's 2.4 gigahertz only, and it's on channel 6 right now. And I've actually just got it hooked up to speedtest.net, everybody's favorite throughput testing tool. So I'm going to go ahead and run a speed test on this channel. We're going to look at this channel to see if the utilization on this channel goes up. We can already see it's bumped from about 47 to 52%, 55%, and climbing 56%. We can see that we have influenced the utilization of this channel. This channel is now being utilized about 61% of the time. Okay, we've just completed our throughput test, and if we look in the waterfall view, I'm going to grab a slightly bigger time span to help us see everything. We can actually see where the throughput test started, which was right here at this point in time, and we can see where the throughput test ended. So we can see exactly how often this channel is being used, and this tells us, okay, this channel is really busy. It's being used more than 50% of the time. Maybe we need to investigate what is going on that channel as the next troubleshooting step. Now, before we do that, I want to go over some common shapes that you might see in the spectrum when you're using a spectrum analyzer. This is what 802.11b looks like. 802.11b kind of makes this curve shape with lobes down each side. And this is a sign that we're using an older, slower data rate like 1 or 2 or 5.5 or 11 megabits per second. And it's also a sign that maybe things could be performing better. In fact, we saw an 802.11b signature on channel 6, and that tells me that channel is being negatively impacted by those slower devices that are talking and eating up all the time on the channel. Now, this is what 802.11g and 802.11n look like. They make a flat tabletop shape, and if you're very, very close to it, you'll see these shoulders down each side. You won't always see those, but if you're very, very close to the device that's transmitting, you will see those shoulders. This tells us that a faster data rate is in use, like 6, 9, 12, 18, 24, 48, 54 megabits per second and beyond. This can be up to about 150 megabits per second in the 2.4 gigahertz band. Now, some non-Wi-Fi devices to keep an eye out for, this is what a frequency hopping baby monitor looks like. And this device is kind of frustrating because it likes to move from channel to channel. If we look in the waterfall view, we can see that this device hung out on channel 5 and then switched over here to channel 9. And it hung out there on channel 9 for about 4 more seconds. We can tell because the time span, or the timestamps over here. And then it hopped all the way down here to Wi-Fi channel 1. And when it did that, it did something really bad. Because if you look closely, there's an 802.11g network on channel 1, and now that baby monitor is potentially interrupting that network. And this is frustrating because it'll move on the channel and off the channel and on the channel and off again, which can be very, very problematic. So we've got to watch out for devices like that. Here's an example of a fast frequency hopping device. This is what Bluetooth looks like. And we can tell it's the same device because we can see that there is the same signature, the same shape repeated in the spectrum over and over and over and over again. They're all the same height. They all look exactly uniform, and so that tells me that this is the same device that is simply hopping all over the spectrum. Bluetooth works by rapidly hopping from channel to channel, almost in a random fashion. You can't see any kind of perceptible. A pattern in the waterfall view typically with Bluetooth. Now, is Bluetooth going to be as big of a problem? No, it's not, because if you look closely, it's blue, which means it's only talking about 10% of the time, maybe 20% of the time here at these lower amplitudes. So typically Bluetooth does not cause a significant amount of interference, although it's often blamed for interference issues. So the last example I want to show you was this analog wireless video camera. These make a very distinct shape. They make 3 distinct spikes in the spectrum, and if you look at the utilization, if you look at the color of this device, we can see that it's talking 50% of the time or more. It's completely blowing up channel 11, so it's not going to permit devices on that channel to talk, and that's going to be very, very problematic. Okay, so let's get back to the Wi-Fi stuff. You remember how we talked about the half duplex nature of Wi-Fi, and now having too many devices on a channel, having too many devices there will limit the amount of airtime that's available. There is a finite amount of airtime available on a given channel, and having too many devices on that channel will eat up all that airtime. We've also got to consider data rates as well. If we've got devices that are using slower data rates, they will take longer to transmit the same amount of data. For example, let's say that we have an Android phone here, and it's relatively close to the access point, so it's able to maintain a nice fast data rate like 54 megabits per second. But then we've also, on the same channel connected to the same access point, we've got another device that's on the very, very edge of the coverage area, so it's had to slow down to a legacy data rate. This is the original data rate for Wi-Fi, back way before it was called Wi-Fi. Maybe we've had to slow down to 1 megabit per second to enunciate to make sure that the access point can hear us. This device, when it talks, is going to take 54 times longer to transmit the same amount of data as the device that's transmitting at 54 megabits per second. The device that's transmitting at 54 megabits per second is 54 times faster, so it will take 54 times less time on the air. So we've got to limit slow devices. We've got to keep slow devices from eating up all of our time on the air and then raising our utilization. And that's where packet analysis comes in. With packet analysis, we can get a really close look at what is happening on a specific channel. We can capture an entire conversation on a channel and see all the activity from all the laptops, all the tablets, all the smartphones and access points, and that's going to show us the details about 802.11 congestion on a specific channel, so we can see exactly what is happening on that specific channel. So this is where we got to make the link between utilization and airtime. When we're looking at a packet analyzer, we're seeing utilization. Utilization is the percentage of time that raw radio frequency activity was detected on the air. Basically, how often did we hear something talking on the air, whether that be 10% of the time or 50% of the time. Then when we move to layer 2, when we look instead of looking at the raw radio frequency activity, when we move to actually looking at what those conversations are, decoding the data that's coming through the air and looking at what's happening, that's when we look at layer 2. And with layer 2, we can measure airtime. We can actually measure how much time those conversations are taking up on the air. Instead of looking at raw radio frequency activity, we can actually look at those conversations. We can look at the data moving back and forth between devices to figure out exactly who is talking fast and who is talking slow. Now, the traditional way of doing packet analysis is with Wireshark. And we love Wireshark. Wireshark is an excellent tool. It's maintained as a labor of love by the open source community, and we're very grateful to them for that. Wireshark is an excellent tool, and if you don't have it, I highly recommend getting it. It's free, and it is a wonderful tool. The problem with Wireshark is that when you take a wireless packet capture with it, it's a bit difficult to visualize airtime usage because it just spits out a giant list of packets. And sure, you can go take a look at each packet, and that might help you troubleshoot some issues on your wireless network, but it doesn't help you understand who is talking fast, who is talking slow, and who is repeating themselves all the time and eating up all of your valuable time on the air. That's where IPA comes in. IPA allows you to take a packet capture and then it parses all of that data out and puts it into multi-layered pie charts so you can see exactly how much time each conversation took up. So all of the time that was used on the channel is represented in this entire multi-layered pie chart. So that represents all of the time that was taken up on the channel. And now we can look at the individual layers to see how much time each network, access point, client, and even what kind of data the client was moving. We can see how much of that time was taken up doing what on the air. So if we look at the innermost ring, the network ring is the innermost ring. That shows us how much time the total network took up during the packet capture. And we can see that during this packet capture that this network called Bronco Guest took up about 2/3 of the total amount of airtime that was used. But let's drill in a little bit deeper. Instead of looking at the entire channel, let's take a look at how much time this specific access point used up. So now we're going to look at the individual access point, which is the next ring out. We can see that this particular access point used up about half of the total amount of airtime on the channel. So that access point and everything connected to it was responsible for about half of the total amount of airtime. We go one more layer out, and now we're looking at the client device. This client device used up about 1/3 of the total amount of time on that channel, the conversation between this client and this access point. So we can see that that client used about 1/3 of the total amount of time on that channel. We can also see what types of frames were in use by looking at the outermost ring. I wish we had more time to go into exactly what these mean today, but for the sake of time, we'll just gloss over it really quickly. There are basically 3 different types of frames: control frames, management frames, and data frames. The short of this is that control frames and management frames are simply management overhead. They just simply allow the wireless network to operate, whereas data frames are the actual data that we're actually moving through the wireless network. And we want to keep our management overhead as low as possible, and we want to spend the most time sending actual data. If you look at the colors around the outside, blue is anywhere where we are sending actual data, whereas anything that is purple or orange shows that that's just where we had management overhead. That's time taken up by management overhead, so you can very quickly see that. Okay, so now I'm going to go ahead and jump into a live demo with IPA. We're going to do the exact same thing that we did with Channelizer, where we're going to take a look. At what's going on in the spectrum, but instead of using the spectrum analyzer this time, we're going to use IPA, and we're going to capture that entire wireless conversation. So I've got an AirPCAP NX. It's a product by Riverbed that allows us to do packet capture in Windows, and I've got it configured to channel 6, and I'm going to start capturing all of those packets that are flying on channel 6. Now I'm going to start that exact same throughput test on my Android tablet here, and one thing you'll notice is that right as we start that, our file size goes up very, very quickly, because now we are capturing that throughput test, that performance test that is happening on the air. So we just finished our download, and now we're starting our upload. And so while that's running, one thing that you may notice is that we also get a total amount of packets, and you can see that jumping by thousands every second. We're up to 21,000 packets now, 22,000 packets. We're capturing a lot of packets. We also do get some invalid packets, but that's okay. That's normal. We don't understand every single packet that we hear. Okay, so now we've completed our throughput test, so we're going to go ahead and stop the packet capture, and now IPA is going to parse all those data frames. It's going to see are all those frames that it heard, all those conversations, going to figure out who talked fast, who talked slow, and who talked the most. Okay, so now we get our multi-layered pie chart. If we hover our mouse over the center ring, we can see which networks took up how much airtime. So for example, if we look at, let's find somebody here, maybe MetaGeek Lab Airport. This is my Airport Extreme that's sitting over in the lab. It took up a little slice of airtime, not a whole lot, but it was just sitting there basically replying to devices that are looking for a new network to connect to, and also saying, hey, I'm a network and I'm here. It really didn't do anything significant. Whereas if we look at MetaGeek, this particular network took up over 1/4 of the amount of total airtime on the channel. If we go one more layer out, we can see that this specific access point, which in this case is called the plank, this specific access point took up all of the airtime on this channel. If we go one more layer out, now we can see that this ASUS device took up about 1/8 of the time on the channel. So this is the client device that talked the most. Now my Nexus 7 is made by ASUS, and so we know that that is the Nexus 7. Now there's a couple interesting pieces of information that I can see here. The most interesting one is that the retry rate was 15%. 15% of the time, this device had to repeat itself in its conversation with the access point. And if we go one more layer out, now we can see the data versus management overhead. So the next thing I want to point you to is this airtime graph along the top. This graph along the top shows us how much airtime was being used over the course of the packet capture. And you can see how much airtime was being used from a percentage standpoint. Now remember, airtime is very, very similar to utilization. It's not quite the same thing, but they're very, very close. They will affect each other. They will cause each other to go up. We can see that throughout the course of this packet capture, there was a couple of times where we hit 55% utilization, but most of the time we were seeing about 30% utilization. We can kind of see the ebb and flow of utilization as the packet capture went on. So now what I'm going to do is I'm going to select our ASUS device. I'm actually going to drill down into it by clicking on it in the multi-layered pie chart. So now what you may have noticed is now we have 2 colors up here in the airtime graph. We can see gray, that's everything that in the packet capture, and then we can see what is currently selected. We've only got the conversation between the Nexus 7 and the access point selected right now, and we can actually see some green where those conversations were occurring. So we can see, if you look closely, you can actually see where we did our upload or our download test. So here's where we did our download test, and then you can see there was a little break in the middle where we really didn't do anything, and then we had our upload test here at the here towards the end. We can also see which data rates were in use. If I come down here to this graph and hover my mouse over one of these pie charts, I can see that most of the time we fell back to 24 megabits per second, but sometimes we actually made it up to 65 megabits per second. Now, one reason why we don't see any of these lower data rates is because we've actually disabled all of the data rates below 24 megabits per second. 1 megabit per second, 2, 5.5, and 11, they have all been disabled, and so we are defaulting to 24 megabits per second because that is one of the lowest rates that is enabled on this wireless network. And that is forcing this device to talk quickly and thus consume less airtime. Now we like IEPA quite a bit. We think it's a really great tool, and if you skip over to the Packets tab, you can actually look at the conversation that is unfolding. But if you're a diehard Wireshark fan, don't worry, we've got you covered. If you click File and click Send to Wireshark, we'll actually take whatever conversation you have selected, or whatever you've drilled down into. If you click Send to Wireshark, we'll take those packets and we'll export them to Wireshark. So if you need to, you can get a much deeper look into that specific conversation to see what exactly is going on. And so that's just a really nice feature that we've maintained complete compatibility with Wireshark in that way, and I just think that's something that's really nice. Okay, so at this time, I'd like to go ahead and open up the floor for any questions. So, Julie.
Yes, thank you, Joel, very much for that wonderful presentation. And it looks like we do have some questions for you. Let's see, first one here. What frequencies do you make spectrum and analyzers for?
We make spectrum analyzers for 2.4 and 5 gigahertz, so the entire 2.4 gigahertz band and the entire 5 gigahertz band. There's a couple of different models out there. The WiSpy 2.4X is 2.4 gigahertz only, and then the WiSpy DBX, it stands for dual band, does both 2.4 and 5 gigahertz. Channelizer focuses on Wi-Fi troubleshooting, and so we work in those two bands.
Great, thank you very much. I got the next question for you here is, let's see. Oops, 1 second here. Questions, hold on 1 quick second.
Sounds like it ran away from you.
Yeah, it did. Where did 1 second there, it's coming right back. Oh. Okay, got him. Oops, come on over here, guy. Sorry about that. I've got it ready to go here.
Great.
Let's see. Let's see, what was my first question? I'm sorry. Let's see. I got one here. Oh, okay. Next question. Does IPA support 802.11ac?
That's a great question. So we bundle IPA with the AirPCAP NX. That's a packet capture device by Riverbed. The AirPCAP NX itself does not support 802.11ac. So if there's any 802.11ac frames, it'll just straight up miss those. It won't see those. It will see all the management overhead because those are transmitted at 802.11n rates. But IPA itself does support 802.11ac. So if you want to get 802.11ac captures, my favorite way to do it is with a Mac. If you get a MacBook Air or a MacBook Pro, anything newer than I think mid-2013 will have 802.11ac, and you can actually take those packet captures natively from within Mac OS, and then you can just move those packet capture files over to your Windows machine. You can use Dropbox or BitTorrent Sync or Google Drive or whatever to get them moved over there. You can do it almost completely automatically. And as for the packet capture tool that I like to use in Mac OS, I like to use AirTool by Adrian Granados. It's a free tool. Be sure to drop him a donation. Again, that tool is called AirTool, and that allows you to get packet captures from Mac OS without any additional hardware. You can just move those over to Windows.
Oh, thank you very much. We've got another question here. Are your devices user-friendly?
Yes, I think so. I think that especially, I think that Channelizer and the WiSpy DBX is by far the easiest to use spectrum analyzer I've ever seen. The colors are easy to understand. The user interface is clean and simple, and the same goes for IPA as well. IPA is pretty much unparalleled in the packet capture world and the packet analysis world for being easy to use and easy to understand because of the multi-layered pie charts. There's lots of other great packet analysis tools out there that I really like, Wireshark being one of those examples, but IPA I think is just a whole nother level of easy to use.
Thank you very much. Joel, are your products manufactured in China?
Some of the components definitely come from China, but the products themselves, the WiSpy DBX, the WiSpy 2.4X, and the WiSpy Mini, which we didn't talk about today, are all manufactured here. They're all assembled and manufactured right here in the United States, actually particularly right here in Boise, Idaho, where MetaGeek is located. So some could say that the WiSpy DBX is made with real 100% Idaho-grown potatoes.
Great, thank you very much. A couple more questions. When picking the best channel, is the information color-coded, and as I change channels, the color will change to notify if it is the best fit?
That is a good question. One tool that we did not show off today is Insider Office. It's very similar to Channelizer in that it works with the WiSpy and it also does Wi-Fi scanning. And one thing that Insider Office does is it will color code based on interference from other wireless networks. And it's a really neat feature. If somebody's partially overlapping with you, it'll actually turn that network red. And if somebody's sharing the same channel, it'll turn it yellow. So, basically yellow means, hey, it's okay. Maybe not the greatest thing, whereas red means that's bad. You really want to get away from it. So that's one thing that Insider Office does. Insider Office also has a recommended channel feature, so it'll just tell you which channel you should put your wireless network on. So that's a feature that is present in Insider Office. Sadly, we didn't get to talk about that one today, but be sure to check out our website to learn more about Insider Office. There's a really good introduction video available on the product page for that.
Thank you very much. And it looks like our last question is, are there new products in your plans?
Great question. We're always working on stuff. I don't have anything to announce right now, but we do have some exciting things coming up that I am looking forward to us being able to talk about publicly. So hang in there. We've got some fun stuff coming up soon.
Sounds great. And of course, with our next webinar, maybe you'll have something for us at that point.
Maybe so.
Looking forward to it. So thank you so very much for answering those questions. And thank you, everyone, for attending today's webinar. Any other questions, please feel free to contact your sales rep or email us at sales@microcomtech.com. If you wish to view any of the products mentioned or shown today, please visit us at www.microcom.us. And remember, this webinar presentation has been recorded and will be uploaded to our YouTube channel so it can be viewed and referenced once again on YouTube. So thank you. Everybody have a terrific day. And Joel, once again, thank you so much for your presentation. We all appreciated it and learned very much here today.
Great. Thanks, Julie.
You're welcome.